everyone and welcome to video number 4 in the Transformers course. In this video, we are going to cover the practical transformer. In other words, we will derive the exact equivalent circuit and understand how it represents the transformer's real-world behavior. So let's start. In the previous video, video number 3, we covered the ideal transformer and its simplified behavior under ideal conditions. I'm going to add for you the link of this video in the comments. In this video, we will move to the practical transformer and develop its equivalent circuit by incorporating the effects of the windings and the iron core. So the question now, what is a practical transformer? Actual transformer or real transformer? A practical transformer or real transformer is a transformer whose operation is affected by winding resistance, leakage flux, and core losses. That one affect the transformer to deviate from the ideal behavior. These non-ideal effects are represented in its equivalent circuit to accurately model its performance. As we can see here, we have the transformer and we have a primary side and secondary side. And in the primary, we have the primary winding, and in the secondary, we have secondary winding. What you said? You said the word winding. What that means? There is a finite winding resistance in both the primary and secondary. So the word winding means that we have resistance. We can denote the primary winding resistance with R1 and the secondary winding resistance with R2. And definitely if there is a current in the primary and secondary, this means that we have a copper loss. So we can say that R1 is the primary winding resistance and R2 is the secondary winding resistance. So now we can represent this transformer as we can see in this figure. We are going to extract the winding resistance outside the transformer. So there will be a primary side and secondary side. So we have R1 and R2. So far we identified the winding resistance, R1 in the primary side, R2 in the secondary side, but if there is a current going through one winding, there will be a flux linkage, or we call it mutual flux between the two windings. But definitely the windings are not perfectly coupled, so there will be a leakage flux. So that one is represented here by the yellow color, phi leakage 1 and phi leakage 2. And we know that the inductance L equals lambda over I, or equals N phi over I, so we can define L leakage 1, which equals N1 d phi leakage 1 by di1, and L leakage 2 equals N2 d phi leakage 2 by di2. So this equivalent circuit can be modified to the iron core will be the ideal part in the middle. We are going to have a coil in the primary side and coil in the secondary side, and there is two bars in between, so that one representing the iron core or the ideal transformer. And the primary side we have a resistance R1 in series with leakage inductance L leakage 1, because this leakage is going to affect the voltage and makes a voltage drop. And similar to the primary side, we have the secondary side, we have R2 and L leakage 2, and that one is going to represent the leakage inductance in the secondary side. In the previous two slides, you covered the primary and secondary winding resistances and leakage inductances. What about the iron core? We noticed that you put that one something like ideal transformer. Definitely the core is not ideal and has a certain or a specific pH curve. So please refer back to video number 5 in the magnetic circuits course. I explained in details what is the eddy current and hysteresis. So there are finite iron losses here and can be represented by a resistance parallel to the core. So in this case, we have a resistance, we can call it R core, R iron, or Re plus H. It depends on the textbook. Some textbooks like to write it as RC, R iron, or Re plus H, eddy plus hysteresis. So we can use any one of them. So we have a resistance parallel to the induced voltage in the primary side. Another point. Definitely the core has a specific reluctance, and in this case, some MMF is needed to drive flux around the core. In the ideal transformer, N1I1 equals N2I2, but in the actual transformer, N1IM, where IM is a magnetizing current which drives this flux, equals the difference between N1I1 and N2I2. And if we have a current and flux, this means that we have inductance, where Lm, the magnetizing inductance, equals N1 d phi m by dim. So in this case, we we can represent the equivalent circuit as we can see here in the figure. We have the primary winding impedance R1 and L leakage 1 and secondary winding impedance R2L leakage 2. And we have the core, which can be represented by R core, and that one reflects the eddy current and hysteresis, and LM, which represents the flux is going to link the secondary side. So we have this one in parallel to the core as well, because that one considered as a load to the source. So finally we reach the transformer equivalent circuit. We call it exact equivalent circuit, not referred to any side. So we have parameters in the primary side and parameters in the secondary side, and in between we have the ideal transformer. So let us identify the parameters and ratings. We are going to start by voltages. So V1 is the primary voltage or source voltage, and V2 is the load voltage or secondary voltage, while E1 is the induced voltage in the primary side and E2 is the induced voltage in the secondary side. What about the currents? So I1 is the primary current or the supply current, and I2 is the secondary current or load current. What about this current? The new current here is called I2 dash. That one is the image of the secondary current in the primary side. We are going to cover that one in details in the next video. So I node is the no load current, where the current taken from the source if the transformer is running at no load. And that one equals the vectorial sum of the core current and magnetizing current, where I core is the current in this resistance and IM is the current in this reactance. So N1 to N2 is the Turner's ratio. So impedance wise, we have R1 in the primary side. That one is representing the primary winding resistance, and R2 represents the secondary winding resistance. And X1 primary winding leakage reactance, where X equals omega L. So L is the leakage inductance. So that one is the primary winding leakage reactance, and that one is the secondary winding leakage reactance, X2. What about XM? So XM is the magnetizing reactance, and R core is the resistance represents the eddy current and hysteresis losses. And definitely that one is the load impedance. Question now, how to solve a circuit like this one? We have a primary side and secondary side, and they are separated by ideal transformer in between. So the primary is connected to a source voltage with frequency F, and the load is connected to the load impedance Z load. So we are going to start by this equation. The Turner's ratio equals N1 over N2 equals A. In the primary side, we have impedance Z1 equals R1 plus JX1, where X1 equals 2 by FL leakage 1. So we can apply Kirchhoff voltage law, where V1 equals E1 plus I1 Z1. So we are going to take this law. I2 dash has a link with the I2 current using the Turner's ratio, where I2 dash equals 1 over A I2. According to that one, we can calculate I node, which is the no load current, equals I core plus IM as a vectorial sum. And at this point, we are going to use Kirchhoff current law, where I1 equals I node plus I2 dash. We need to move to the secondary side, where E2 equals 1 over A E1, and from this one we can calculate V2. But R2 plus JX2 represents the impedance in the secondary side, where X2 equals 2 by FL leakage 2. So in this case, V2 and E2 are linked by Kirchhoff voltage law here, where E2 equals V2 plus I2Z2, and V2 equals I2Z load. So we notice that one is not easy analysis and time consuming. What do you mean? Although the exact equivalent circuit shown here gives the accurate presentation of the real transformer or actual transformer, it is not usually preferred for calculation because it contains quantities in both the primary and secondary side separated by an ideal transformer. This makes the analysis somehow complicated. So what is the solution to simplify the calculation? We are going to use what we called referred equivalent circuit, and this is what we are going to cover in the next video. So what will I watch in video number 5? In video number 5, we are going to cover referred equivalent circuit. See you in the next video.